Hi guys, in this video we're going to be looking at a new method for solving equations which we call row reduction. So what we're going to be doing first of all is solving two equations with two unknowns. So as you would have seen today on Friday, this is often really important when you're solving the intersection point of two lines. And also we'll be using this with 3x3 matrices or three equations with three unknowns when we want to solve the intersection of two planes. So let's just do a little example. So let's say we've got two equations, 3x plus 4y equals 17 and x minus 2y equals 9. So what we did today, we solved that using elimination, and that's relatively straightforward most of the time. Row reduction can be a faster way of doing this, but it also, when we're trying to visualize what's happening with the lines, it gives us an idea of what's happening with the lines. So what we do to do this is we actually set up a matrix. So we call it an augmented matrix. Augmented meaning two things joined together. And what we're going to join together are the coefficients of the left-hand side of the equations with the right-hand side of the equation. So we're going to draw the matrix like this with a little line. That's the augmented part. And on the left, I'm going to put in the coefficients. So 3, 4, 1, and -2. The 1 just comes from the x on its own. And then the right-hand side of the equations is going to go over here. So 17 and 9. Now, what we're going to do is we're going to name these two rows of the matrix, row 1 and row 2, and they correspond to the two equations. Now, there are a few things that we can do to the rows in order to solve the equation. I'm just going to bring those up now. So the three possible things we can do, I'm just going to go through those one by one. First of all, we can swap rows, and the way we would write that is that row 1 becomes row 2, or row 2 becomes row 1. So we use a little arrow to mean becomes, kind of like a chemical equation a bit. We can multiply a row by a scalar. So if we wanted to multiply row 1 by a value, we would write row 1 becomes, let's say, 2 row 1. And then we would change row 1 so that every number was double. And then the final thing we can do is we can add or subtract multiples of another row. So let's say what we wanted to do is we could take row 2 and say that that becomes row 2 plus 2 lots of row 1. That's how we would write it. So those are the three different things that we can do. Now, what's the actual goal? Well, the goal, in the case of two equations and two unknowns, the goal is to make this number here 0. Okay, and you'll see why when we get to that. But if we can make that number 0, then we're able to solve the equations. So now let's do that with the matrix that we've started with here. So what I'm going to do is I'm just going to draw it up again. And now what I need to do is I'm going to modify row 2. So I'm going to say that row 2 is going to become 3 lots of row 2. So I'm multiplying by a scalar. And then I'm going to subtract row 1. And the reason I'm doing that is that 3 lots of 1 take 3 will give me 0. So remember, my goal is to make that number in the bottom left corner there 0. So row 1 is unchanged because I'm not doing any operations on that. This number here will become 1 times 3, which is 3, take 3, which is 0. Now I'm going to do -2 times 3, which is -6. Take 4 is -10. And then I'm going to do 9 times 3, which is 27, take 17, which is 10. Okay, so now I've achieved my goal. This bottom left corner is 0. So what I'm going to do is I'm actually going to pull out this equation. So from that, I can say that -10y equals 10. So I'm going back to where I got this from. this becomes the coefficient of y, and this becomes the right-hand side. So in case that doesn't make sense, that first row are the coefficients of x, the second row are the coefficients of y, and the augmented part is the right-hand side. So negative 10y equals 10, and of course that means that y equals negative 1. And then what I can do is I can just go back to my original equation and say that x minus 2 lots of negative 1 is 9. So x plus 2 is 9, or x equals 7. So I've been able to solve that equation using this, this row reduction technique. You'll probably be thinking at the moment, that's not much faster than elimination. And for 2 equations and 2 unknowns, it's probably true. But it's important for you to be able to know how to do this, because then when you move up to 3 equations and 3 unknowns, this methodology becomes really very powerful indeed. Okay, so how does all of this relate to lines? Let's find out. So if we're talking about 2 lines that we're trying to solve for, like we were on Friday or today, there are 3 possibilities basically if you're trying to find the point of intersection. So the first one is that the 2 lines intersect somewhere. Now keep in mind we're just talking about 2 dimensions for now. When we go into 3 dimensions, there's one more possibility, but we'll talk about that when we get to 3D. So in 2D, the lines might be intersecting. And what that means is, in terms of finding the points of intersection, it means that there'll be one unique solution. One pair of x, y coordinates where the 2 lines meet. So what that means is when you're doing your row reduction, what you'll get is basically what you just saw in the example. You'll have, some value A1, A2, B1, some other value here, which we'll call A4, and this will be B2, and you'll get a 0. So all of those values don't equal 0. Of course, A1, B2, and A4 are not equal to 0. This is what you'll be able to reduce the matrix to. The next possibility is that you've got 2 parallel lines. Okay, they don't really look parallel, but I'll draw some triangles on here to indicate that they're parallel. Now, what that will mean is that there are no solutions possible. And what you'll find when you try and do a row reduction in this case is that you'll get your top line will look okay, but no matter what you do, whenever you try to reduce the bottom line, you'll get 2 zeros here and then some sort of value here. Now what that's actually implying is it's basically saying that 0x plus 0y equals a non-zero number, and that's not possible. So that tells us that there's no solutions. Okay. Now the final possibility is what we call coincident lines. Now that's kind of like parallel, but the 2 lines are exactly on top of each other. They lie exactly on top of each other. And in terms of actually solving for the points of intersection, this means that there's infinite solutions. Okay, because no matter where you go on these 2 lines, that will be a solution. And what you'll find here when you do the row reduction is you'll get A1, A2, B1 on the top, and then your bottom row will become all zeros. And that's basically because if you try and subtract the first equation from the second, because they are essentially the same equation, you'll find that you'll just cancel out the entire bottom line. If you sort of think about what it means, well, the bottom row there is telling you that 0x plus 0y equals 0. And no matter what value of x and y you put in there, that's always going to be true, because 0 times whatever is always going to be 0. So there are infinite solutions in that case. So from doing the row reduction, you can actually tell what type of situation you're dealing with. Okay, I hope that makes sense. Good luck with the questions on this. Thanks for watching.